Hey guys, this is a video for lesson 2-1 and 2-2. Okay, so in 2-1, what I want you to learn is to identify the rate of change and use it to write an equation, and then use that equation to find solutions. Okay, well, what's a rate of change? Rate of change is the same thing as slope. We're talking linear equations here, so slope. It is the m of mx plus b, and you would find it in a word problem with words like per, each, and every. Or it could be context clues. So we hear rates of change in our everyday life all the time. So if a car's speed limit was 45 miles per hour, okay, miles per hour, or you could say that, you know, somebody saved $20 every week. Okay, and I meant to capitalize that every, because that's one of the key words. Or I could say each pair of socks is $4. Okay, so those keywords help you identify the rate of change. I will also point out that you can see independent and dependent. Okay, if you can think about something in terms of the word per, okay, it's your dependent is going to be the same as what's in front of the per, and your independent is going to be what's after the per. Okay, so if I said this $20 per week instead of $20 every week, same thing. So this cost is going to be the dependent. Money is my dependent. Week is my independent. Now each pair of socks is $4. It's worded a little bit differently. So it's $4 per socks, per pair of socks. So money would be the dependent. I just reworded it so that I could use the word per. So if money is the dependent and the pairs of socks is the independent. Okay, so if you can rewrite it in your head or rethink it in your head with the word per, then that helps you with your dependent and independent. Okay, so given a linear function, we're going to identify the rate of change, the input, and the output. Okay, when we're talking about input, we mean things like x values and your independent variable. Okay, output would be your y values, okay, which we also know now to call f of x. And those are your dependent values. Those are your outputs. Okay, so Belinda is making greeting cards. She makes 4 cards per hour. So I see that key word per. So 4 cards per hour. And you can see here it says the rate of change is 4. The function c of t equals 4t. Now I want to point out that that is in function notation, and generically it could have been written f of x equals 4x. Okay, so, and that would have been fine. That's the generic version. Well, where do the letters c and t come from? Well, t is for time because we're using hours. Okay, hours is our independent variable. It is our input. Okay, so which is down here. We'll cover that. Okay, so t, that's our input. It's the same thing as our x value. And the 4 is next to the variable, and that's where the rate of change is located in an equation. It's right next to the variable. The rate of change multiplies your input variable. So whether that's x or t or whatever. Okay? Then our output is the result. So the whole thing, c of t, and I'm going to kind of overshadow that t right there. Okay? And for t, the whole thing, that's our output. Okay? So I would argue that they say that for t is the output, and I would say that symbolically we would represent that as c of t as well. Okay? So going down to the next question. A teacher graded quizzes and found that she graded 12 quizzes per hour. So I hear that 12 quizzes per hour. I see the word per. So my rate of change, which I abbreviate ROC, is 12 quizzes per hour. With 12 being the value. Okay, the function, and I see that rate of change in its position right in front of the variable. Okay, Q of t equals 12t represents the number of quizzes as a function of time. So t is our input. Okay, and our output is putting it together, 12t. Or Q of t. Okay? And I would write both. All right, filling in a table with a rate of change. So we're going to use this airliner in both lesson 2.1 and 2.2. Basically, we're going to talk about the plane as an overview here. We're going to talk about the plane taking off and going up. Okay, then we're not going to talk about it flying, but then we're going to talk about it in 2.1 coming in for a landing. Okay, so we're talking about the takeoff for right now. Okay, a 747 airliner has an original climb rate, says the word rate, of 1,800 feet per minute. So we can identify the rate of change as 1,800. Okay, until it reaches a height of 10,000 feet. Okay, so when we write that function, we're writing it with the 1,800. And when I say the word function, the word function and the word equation are somewhat interchangeable. Okay, so rate of change is 1,800 feet. All right, so let's do independent and dependent quantity. And I see something per something. Okay, so what's in front is the dependent, and what is after the per is the independent. Okay, now feet and minutes are units. Okay, so for independent, my unit is minute, and for dependent, my unit is feet. So what quantity is asking is more generally, what are we measuring? So minutes is a unit of time. And feet is a measure of height for the plane. We're measuring the height of the plane. Okay, so when we write a function for this, we can write it a few different ways. You can write it generically, f of x equals 1,800 times x. So that's generically, that's fine. Or you can personalize it to the question by using the first letters of what we're talking about. And we can kind of mix and match, okay? In place of the F, you would use, say, H for height, or you can keep the F and keep it F of feet. Okay? The X would be replaced by one of these letters, T for time, M for minute. I'm going to say a lot of times you're going to see T. Doesn't matter. The important thing is, if you're going to use T for a variable, make it the T with a tail so it does not look like a plus sign. Okay, and I also make it full size. A plus sign would be would be small, and a T would be larger size. Okay? Okay, so then we have this chart to fill in. All right, now if we think about an airplane, and it's sitting on the ground. Well, how high is the plane at time 0 when the plane has not taken off yet? Well, it's not any height. There's no height at all. It's 0. No feet off the ground. It's saying it's going to go up by 1,800 feet per minute. So if 1 minute goes by, that's 1,800 feet. If 2 minutes has gone by, guys, we can think of this a couple of different ways. One way that you could think about it is if I've gone up by 1 minute, then I'm adding 1,800 more feet, which makes 3,600 feet. The other way to think about it is to say, okay, well, 1,800 times 2, 1,800 T stands for minutes, 2 minutes, sub in, and that would equal my 3,600 feet. Okay? Now, be careful because the next row, we're not going to simply add on 1,800 more because on this side, okay, so 0 to 1, we went up by 1 minute. 1 to 2, we went up by 1 minute. But 2 to 2.5, we only went up by a half a minute or 30 seconds. So we're not going to go up by 1,800 again. So if we only went up half as much, that would be adding 900. So adding 900 would be 4,500. And then we went up by a half again. So we're going up by 900 again, and that would be 5,400. And then we're going up by half again. 6,300. And at 5 minutes would be 7,200. And I believe that's the bottom of the chart, but let's just check. Okay. Nope. All right. So 7,200. All right. So basically what it's saying here, down here, the expression is T, and that's your input. Your output is 1,800 T. All of the values above that in the chart could be found by taking 1,800 and multiplying it by the input. So this 7,200 could be found by taking 1,800 and multiplying that by 5. Okay, and that would give me my output of 7,200. Okay. Let's practice that again. So we've got Miguel, and he's riding his bike to lacrosse practice at a rate of 7 miles per hour. So I see the word rate, which you don't always get, so it's kind of a bonus. And it says 7 miles per hour. So my rate of change is 7. Okay, so, and then I see my units, dependent, independent. So my units are hours, and that's a unit of time. And my dependent is miles, and that's a unit of distance. Okay, so the expression for the input is going to be the letter we're going to use. Let's use H. Okay, and for the output, that's going to be 7H. Okay, as a function, we could be very generic. We could say f of x equals 7x. But since we have these values here, we should probably make it more personal to the equation. We could do d of h or m of h. Doesn't matter. Okay, d for distance, m for miles, either one in terms of hours h. All right, so going on, Miguel is riding his bike. No time has gone by, so common sense says he is still at home. He hasn't gone anywhere yet. No distance yet. Okay, and then to make the jump from 0 to 0.5, that means he's only gone a half hour. So if he's going 7 miles for 1 hour, if he only goes a half hour, that's half that distance. So that's going to be 3.5. 1 hour is 7. 1.5 would be like, okay, so 1 was 7, a half hour was 3.5, so 10.5. But also you could come over here and say 7 times 1.5, and you could get your 10.5 that way. Okay. 2 hours is going to be 14 miles. Okay. All right, so finding solutions algebraically, we've kind of done that. That's where I'm subbing in, like I did right here. But I'm going to take it a step further with some notation things. Okay, so if we have a function that says f of x equals 12x, what f of 3 means is that x equals 3, and so we should sub 3 in for the value of x in the equation. So in this one, that would mean I would take 3 and put it in the place of x. So 12 times 3, and I would get an answer of 36. Okay, so let's jump down here to these examples. So f of 8, so we have f of x equaling negative 10x. If I asked you what's f of 8, you would sub in 8 for the x. I saw it subbed in here, so I will sub it in to that x. So f of 8 equals negative 80. Okay, so my function is f of x equals 1.2x. This is asking, well, what's f of 3.4? So I will sub in 3.4 for x. And I will get an answer of 4.08. Okay. Last one. Negative 10 times negative 2.35. So f of negative 2.35 equals positive 23.5. Now, you might be saying to yourself, Mrs. Andrews, I noticed that you're carrying down the f of every time and including the f of the number in the answer, in the box that I'm drawing around the answer. And that's not an accident, and it is something you should be doing. It makes a complete sentence out of your answer. Okay, here's the reason for that. If I switch this up and I'm asking for f of 5, then I'm subbing 5 in for x, and I will get a completely different answer. So if all I put is negative 50, I'm not saying, well, why is it negative 50? Okay, so we have to put f of 5 equals negative 50 and include that together. It's like answering in a complete sentence, which I know that's what they're trying to get you to do in English class and social studies class and maybe other classes as well, is to answer as complete sentences. Okay, so we can find solutions algebraically, which means using math and adding and subtracting and multiplying and dividing, but we can also find the solutions using a graph. Okay, so it's the directions here says use the graph to determine how many minutes it will take the plane to reach each height. So this is saying h of t equals 5,400 feet. So that means that the height is 5,400 feet, and that is located on the y-axis. Okay, so we're looking at how many minutes that's going to take. How many minutes would be on the x-axis because it is our independent variable. So if I pull this down so we can see the whole graph, I would find that y value of 5,400, follow it across, and it seems to hit the graph right about here, and I will follow it down to the x-axis, and that is at 3 minutes. What I want to caution you with is in this particular example, this is a graph of the exact same data we used a couple screens ago about the plane. So at 5,400 feet, 3 minutes. That is an exact data point, and we can say with quite a bit of confidence that 3 is the answer that would be exact. But otherwise, we're going to be making some estimations in here. You can't look at where it crosses on the graph and know exactly the value, because even though it appears to cross where the 3 is and the 5400 is, if it was 3 minutes and 1 second or 2 minutes and 58 seconds, that would not look dramatically different on the graph. We just don't have, you know, that kind of accuracy on here, okay? All right, 9,000, if I look at my axis here, 9,000 is not there. It's above, it would be somewhere above 8,100. Well, it turns out 900 more. This graph is counting by 900s. So if I went up 900 more, the very top line of the graph, even though it's not labeled, is 9,000. So when I followed this across, okay, following across and then following down, and I can see that appears to be about 5 minutes. Okay, now I use the little squiggly to denote that it's about 5 minutes. If we go back to our chart, we don't have 9,000 on there, do we? Nope, we stopped. Y'all, I caught a mistake. I caught a mistake. That's not going to be 7,200. This went up by 1.5. So 1,800 times 5. If I had typed that in, is 9,000. So guys, I'll tell you, I'm not a professional videographer, and if I make a mistake and I catch it, I will fix it, but I will not remake the video. Just be aware. Okay, if you ever find a mistake in my videos, let me know, because most of the time I catch it, but if I don't, let me know. So that should have been 9,000. Which is 5 minutes. Okay, here's what I'm talking about with having to estimate. 3,150 is not, for sure, one of our values in our chart. So 3,150 is about part way, somewhere maybe about halfway between 2,700 and 3,600. So if I follow that across, and then I hit the line, and then I follow that down to see how many minutes that is. Well, it falls between the 1 and the 2, closer to the 2. I'm going to say it looks to be about 1.75 minutes, okay, or 1 minute and 45 seconds, somewhere about there. Okay, 4,500. If I follow that across, there's where I hit my graph. If I go down, it looks like, oh, let's see, that looks to be about 2.5 minutes, and I believe that is one of our data points in the chart. Yep, 2.5 minutes. Okay, so we've got a graph here, but they're estimates. It's not an exact answer. Okay, it can be. Like, we have the data to prove that 5 minutes and 3 minutes and 2.5 minutes. I'll take the tilde away. I'll make that an equal sign. Okay, we have the data in the chart to know that 3, 5, and 2.5 are accurate. But that 1.75, That was my estimate from the chart, and I would have to solve algebraically if I wanted to know if it was exactly 1.75 or not. Okay, this time, so just to sum up, this time we're looking at the y-axis, and for whatever reason that y is not there. Okay, and what we are trying to find is an x value. Okay, switching gears, we're going to launch right into lesson 2-2. And in 2-2, I want you to identify the parts of a linear equation modeled in given situations. Okay, so input, we talked about last lesson. It is your independent variable. It's your x. It's the whatever letter you put inside the parentheses. Okay, your output is your dependent variable. It's like your f of x or your y values. Rate of change, that per, each, every, it's your m, it's your slope. Today the big add-in is Y-intercept. It is the number that you start at. It happens one time, and it is represented by the letter B in y equals mx plus b, or f of x equals mx plus b. So m is your rate of change, b is your y-intercept, and they are numbers. Okay, so we're still talking about the airplane, and so now the plane has been flying for a while and it's time to land. So the plane is at 36,000 square feet. This is our starting value for this point in the problem. That is our B, that is our y-intercept, all those things. Those are all interchangeable words. The plane descends at a rate, we see the word rate, of 1,500 feet per minute until it lands. So that is our rate of change. Let's make that a little bit bigger. Okay, so compare this problem situation to the one in 2-1. How are the situations the same and how are they different? Well, they're the same because we're still talking about the altitude or the height. I think I used the word height before. I come from a pilot family, so altitude makes more sense to me, but height of the plane per unit of time. So our dependent and our independent variables are the same. What's different this time, two things are different. One, the rates of change, not only are they different numbers, this is 1,500 and not 1,800, different numbers, but also this rate of change, we're going down. So this rate of change is actually going to be negative. It doesn't say a negative sign in the wording, but because it's descending, descending is a word that's going to help us know that that 1,500 is going to be negative. So the rate of changes are different numbers, okay, but we're also going in different directions, down instead of up. And we're also having a different starting point. Okay, in the 2-1 airplane problem, we were starting on the ground, so that was 0. Here we're starting all the way, we're up in the air already, it's at 36,000 feet. Okay, so things are still the same. This is still minutes and feet, time, and height. Okay, but at the beginning of this problem, we're starting out at 36,000 feet. So our rate of change is negative 1,500. Negative because the plane is descending. It is going down by 1,500 feet. Okay, so if we're at 36,000 feet, and it looks like 0 to 2, 2 minutes have gone by. If 2 minutes have gone by, then that's 3,000 feet that we've gone down. So that would be if I take off 3,000 feet, that's 33,000. 2 to 4, 2 more minutes have gone by. So we're going to take off 3,000 more. 6, 3,000 more. Okay. So what we're going to do at this point is we're trying to figure out now how many minutes would it be to get to 18,000. How many minutes would it be to get to 6,000? Okay. So we'd have to figure out how many times have we dropped 3,000 or 1,500, but I think 3,000 is going to continue to work. And you know, how many minutes is it going to have to go by? Like, I can't put an 8 here. An 8 would not go here because this 27,000 down to 18,000, this did not drop by 3,000. In fact, that dropped by 9,000. So guys, basically it dropped by 3,000 3 times. So if it dropped by 3,000 3 times, then this side is going to go up by 2s 3 times. So 8, 10, 12. To go from 18,000 to 6,000, it went down 12,000. There's a 12,000 foot difference there. So that's going 4 times. 4 3,000s it went down by. So I'd have to go 12, 14, 16, 18, 20. And that's how I would get, that's one way I could get that value. Okay, so we have a starting value. So let's get into writing the function for this. Okay, so we're going to write a function. So our feet in terms of minutes, feet in terms of minutes equals our, remember we're going for an mx plus b. Let's start generic. Yeah, let's start generic. F of x equals mx plus b. So my m, my rate of change, is negative 1,500. X. My b is that starting value. Where did we start? We started at 36,000 feet. Okay, so now we can kind of play with the function. Okay, it says g of t up here, and I suppose if the directions say g of t, then we can use the g, but that's silly. Okay, we're not going to do g. All right, we're going to do h of t. So h of t, height in terms of t. The reason why they do g, just so you know, is because we're writing a second function about the same thing. So if f of x represented the first function about the airplane, and now we're writing a second function about it, they're using the letter g because g comes after f in the alphabet. Okay, so that's where the g comes from. So I'm just going to take it a step further and say h of t equals negative 1,500, but since I use t in the parentheses here, I need to use t here, plus 36,000. Okay, so that is our function. Graph the function using points from the table. Okay, so I'm going to have to flip back and forth a bit here. So we started at 0 at 36,000 feet, so I'm going to draw a dot there. The next value from the table was 2 and 33,000. So 2 and 33,000. 4 and 30,000. That's about halfway. When you draw these dots, this is a linear function. Those dots should be pretty much in a row if you're estimating locations of putting those dots correctly. 6 and 27,000. Whoop, wrong way. 12 and 18,000. Still went the wrong way. 20 and 6,000. Okay. Now, this is not a discrete function because even though we did not graph a point for 8, I mean, it's not like the plane dropped out of the sky or didn't exist at 8 minutes. So this is a continuous function, and I would recommend using a ruler to connect these. And the dots wouldn't line, the only reason the dots don't perfectly line up is because, you know, a human drew these dots, not a machine. So I'm going to approximate that it would land about there. Okay, and just as we learned yesterday, let's see, lesson 2-1, solve the following by reading the graph. So the directions are specifically saying reading the graph. So f of 8, that whole subbing things in, we're not doing that, okay, because we're reading the graph. Remember that that's the x value for 8. So I'm going to come to the x-axis and find 8. We're basically reading the graph the opposite direction from the lesson 2-1. We're starting at 8, working our way up and going across, and finding that it appears to be around 24,000. Could be 24,001, you don't know, but that's the estimate. Okay, now the second one, there's still an x here. So if there's still an x here, then this 14,000 is a y value. And I'm going to take that and I'm going to follow the chart down to 14,000 on the y, the graph on the y-axis to 14,000, which should be halfway between 12 and 16,000. Follow that across, follow that down. And that appears to be around 13 minutes by the way that I drew mine. Okay? Could be 12 and a half. Could be 12 minutes, 58 seconds. Okay? Impossible to know exactly just from looking at the graph. Okay? Okay. So let's just use word problems and just practice identifying the parts of a function in context. So Joe has $50 from his birthday. He also works a job where he earns $100 per week. The situation is modeled using the function m of w equals 100w plus 50. So the equation is given to you. Okay, we just have to be able to identify the parts. Now I want to identify the parts both from the context of the question and the function, because technically what we're aiming for is for you to not need somebody to tell you what the function is. You know, we want to get to where we can write a function without being told. So I'm going to just show both. Okay, input. Input is whatever X is. So W is your input. Which in this case is weeks. Output, a couple different ways you can write it. The output is the whole thing after the equal sign. 100W plus 50. The whole thing. Or M of W is the output. Rate of change. So I see the word per in context here. So 100 is my rate of change. $100 as a rate of change is also right in front of the variable. So you can always tell the rate of change based on where it is in the function. Whatever number is right in front of the variable that multiplies the variable is the rate of change. Okay, and Y-intercept. The Y-intercept is located as the number that's a constant, okay, a number that does not have the variable. And from the context of the question, it's that $50 he started out with from his birthday money before he started earning money. That was his starting amount of money. So he had $50 and then he got a job where he's earning $100 more every week. Okay, so that's how, if you did not have the equation given to you, that's how you could write it. You could say, okay, I want an equation that's in a form of f of x equals mx plus b. So m would be that 100, b would be the 50, and x is my weeks, and the M for money goes on the outside. Now, some of you may question, like, well, if he started off with $50 and then added $100 per week, is it okay to write that backwards? Well, sure it is. You know, the commutative property of mathematics allows us to change the order, just like if I had 1 plus 2 equals 3 and 2 plus 1 equals 3. It allows me to do that. But what I would just, until you really get strong with writing linear equations, we're focusing on this format of mx plus b and in that order. So I would highly encourage you to do the slope, the variable, and the y-intercept in that order for your functions. Okay? All right, number 2, Amber's fish tank has 150 gallons of water in it. She dumps it at a rate of 10 gallons per minute. The situation is modeled using the function g of m equals negative 10m plus 150. So here again, inputs are variables. That's the m. It's in the parentheses. And that stands for minutes. Our output is the whole expression, negative 10m plus 150, or gallons in terms of minutes. Okay. The rate of change. Rate, 10 gallons per minute. Now I see the 10, but it has a negative in front of it. It has a negative in front of it because she's dumping it. The water's going out. There's going to be less and less water in it as time goes by. Okay? The y-intercept, how much did the tank have to start with in it? It had 150 gallons to start with. Okay, and then you're going to have some homework questions that are going to ask you to do something similar to what we did in 2-1. In 2-1, I asked you what f of a particular number is. Like there would be a number here instead of x. This is saying f of x is the worst bracket ever. F of x equals 16. So that means that over here, we're going to take f of x out and sub in 16. So 16 replaces f of x equals 3x plus 10. It does not replace x, it replaces f of x. So I'm going to subtract 10 both sides because now this is a basic two-step equation. 16 take away 10 is 6 equals 3x. Divide by 3, divide by 3, and x equals 2. So what is this really asking for me to do? What it's asking me to do is what's the value of y when, what's the x value when y is 16? Remember that f of x and y are the same thing. F of x is the same as y. So if I took this away and put y here, and I took this away and put y here, it's mean take 16 and put it in the place of y. So you got to think of it like that. Sub in 16 for f of x, and solve, you end up solving a basic two-step equation. Okay. Our second example. So m of t equals 14. So I'm going to sub out m of t and sub in 14 equals negative 20t plus 54. Now I've got a two-step equation where I'll subtract 54. Take away 54 is negative 40. Divide by negative 20. And t equals 2. All right, let's put this together. A pot of water starts out at 35 degrees. That's my B. And increases, so positive, 7 degrees every minute. So that means that 7 is my rate of change. When will the temperature be 100 degrees? So, writing a function, we're talking about minutes, and we're talking about the temperature in terms of minutes. So 7 times every minute, it's going up 7 for every minute, and it's starting out at 35 degrees. So that's our function. Then the 100. The 100 represents temperature. So M stands for minutes. We're not going to sub in. This is not going to be T parentheses 100. This is T of M equals 100. Temperature equals 100. So I'll put 100 in the place here. And then solve. And this is going to come out a decimal. So 65 divided by 7. It's about roughly 9.3. It's the calculator fills the screen, 9.28571, blah, 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 blah. We're going to round it about 9.3 minutes to reach 100 degrees. Okay. Thanks for watching, and I'll see you next time.